What happened to the rest? Any question about the project? Let me show myself at least. Any question you may have? Okay, let me start as the other people slowly show up. Can you hear me, please?
Yes, sir.
Good, sir. We were in chapter 6, and as we mentioned, the objective of this chapter when we finish, hopefully today, is to understand the physical mechanism of convective heat transfer, and that we mentioned to discuss what that means, convective heat transfer. We classify them. We mentioned it should be natural, or we call it free convection, forced convection, and we were trying to visualize how the velocity and temperature profile will develop as flow over the surface. Again, we limited in this discussion to flow over a plate that be able to understand exactly how what's happened. Then we show you again when it's between two layer of a plate, how the velocity profile will develop. Therefore, we have some idea of visualization how actually this take place. And we try to gain knowledge of the dimensionless number. As we mentioned, this dimensionless number will help us trying to really understand the problem. For example, if we talk about the flow, if it's laminar or turbulent. Therefore, we use the Reynolds number as indicator. Then we had a Nusselt number. That actually a Nusselt number shows the convective heat transfer to conductive heat transfer within the fluid. Okay, the difference between Nusselt number and Boyer number. It was Boyer number. We were talking about the conduction inside the solid. Okay, and we had also the Prandtl number. Again, the Prandtl number shows the momentum, the ratio of momentum motion to the heat transfer motion. Therefore, this is now we are dealing with the fluid. There is a movement of the velocity, momentum, and also there is heat transfer. And it was indicating when we can use this one as indicator when the convective heat transfer is important compared to conductive heat transfer. Most of the time, probably we can ignore the conduction because the conductive heat transfer is so much higher than conductive. And then we discussed about, again, this is you have some idea about the laminar flow and turbulent flow. Again, then we try to write equation that trying to study the mass transfer, continuous equation, momentum transfer, and also heat transfer, okay? And based on that one, last lecture or the lecture before, we developed a differential equation that shows these three processes that we have. Mass transfer equation, we wrote the mass balance equation. Based on that one, we were able to find the relation between the velocity u and v. And then we wrote a momentum equation that we were trying to find the velocity profile within the fluid. And then we used that velocity profile to find out the temperature profile in the fluid. Again, the focus is not how to solve the differential equation. That's, I hope if you are interested in continuing education, probably you can take more advanced courses in mathematics and fluid mechanics to do that, okay? But at least in your textbook give you an overview. At least you have some understanding of that problem, okay? Again, we assume somebody has done that problem, solved that differential equation, have been able to find the solution that we needed right now. And then we normalize the convective equation and obtain a sort of heat transfer coefficient, because again, we find the solution for the momentum equation, and if you remember, we were able to find friction factor, and then using the similarity, we use also find a heat transfer coefficient, okay? That was that we're trying to understand this course, okay? Again, here, the whole idea, we use this, through the solution of this problem, we use the analogy between heat transfer and mass transfer and so on, okay? And to continue that discussion, again, the whole idea here, you have to get a general idea about the convective heat transfer process. Here they give you with some fundamental as we go ahead, chapter 7 and 8 and 9, 7 and 8, usually we just use the correlation, but here at least to help you to understand the physics of the problem, because they try to explain the flow of a flat plate that you can visualize and understand the physics behind it. Because later on that the similar problem of flow over a sphere, okay? But that's difficult to show at visualization, okay? As I mentioned last lecture, we wrote this continuity equation, okay? That was based on writing simple mass balance equation. We developed a momentum equation. That's exactly we did it. And then we tried to normalize this equation. Again, I'm using this simple approach here. And when we convert this equation to this one, dimensionless number, you find there is a velocity dimensionless, length dimensionless, all of them is dimensionless, and we have one term here, that this equation that shows this is depend on this factor. And this factor, it was a Reynolds number that we know that obtained, okay? Therefore, this was based, we obtained this equation based on the writing a simple energy momentum equation. Therefore, this is one of the factors we find that affect the solution, okay? Then we do the same thing for convective heat transfer. Again, we're dealing with the forced convection, because we're dealing with fluid is moving and there's external force. Therefore, we wrote this equation again based on simple energy balance equation, and we normalize it the temperature. Therefore, here the temperature of the wall, the temperature of the fluid, and here the temperature of the fluid at every point. Okay, and then we normalize this equation again based as we did for velocity and temperature. We end up this temperature, and we find another important parameter that shows Prandtl number. Again, the Prandtl number indicate which one is dominating. The momentum motion is dominating, or the diffusion by conduction is dominating. Okay, therefore that was kinematic viscosity or thermal diffusivity. Okay, therefore now we have another dimension number here that we presented to you earlier. Okay, therefore that's the idea. We're trying to use this dimensionless to find that. Therefore we know, again, just for your information, Reynolds number representing a ratio inertial force to the viscous force. We mentioned this one last building science, and also we have shows the ratio of momentum diffusion to thermal diffusion. This depends on the conductivity, and that's depend on the viscosity. Okay, this again, this shows which one is dominating. Okay, that's the Prandtl number that we have. Okay, for example, for a liquid metal, because the conductivity is very high, therefore this is less than 0.1, less. Okay, for air is around 1 or 2. Okay, therefore that's representing the physical phenomena of the motion.
Sir, could you repeat for the Prandtl number? You're comparing which and which?
On the top, you can see at the slide, it mentioned kinematic viscosity. Kinematic viscosity is viscosity divided by density. Therefore, this shows the motion of the because of the viscosity phenomena that we have. Okay, and here we have alpha. We call it thermal diffusivity. And if you look at this one definition, we have Cp, you have K, and that's represent effect of this Cp and K. Therefore, this represents the ratio of two type of motion: motion by momentum, the fluid by momentum inside, and this is by energy, by conductivity. Okay. Therefore, that's represent which one is dominating. In case of the liquid metal, with dealing with a material that has very high conductivity, then you expect the Prandtl number to be low. Okay.
Okay. Okay. Thank you, sir.
No problem, sir. And then we continue here. In general, when we try to simplify, and you will see it later on, this is just a general information for you. We will see chapter 7 and 8 and so on. We can write the general equation of Nusselt number is a function of Reynolds number and Prandtl number. And we define again, Nusselt number is a ratio of convective heat transfer to conductive heat transfer, H over K over L. H represent convection, K over L represent conduction, okay? In general, the equation is in this format. We write it down in the format of Nusselt number is a function of Reynolds number and Prandtl number. And when we will see it again, and we saw it last lecture, for laminar flow, this is to power 1/3. In case of this is 4/5, okay? But this is a general equation that we're saying. This is the general form. And in general, we show them Reynolds number to power n and Prandtl number to power m. But this is the function we are trying to say, okay? This is general information. As you know, this is representing kinematic viscosity, K conductivity, and so on, okay? And H heat transfer coefficient. This is just for you to see how the Nusselt number is depend on the motion of the fluid, the Reynolds number that we have, how fast fluid is moving, and also the characteristic of that fluid. This is only the characteristic of the fluid. It means is representing physical properties, conductivity, density, specific, and so on, okay? We solved this problem last lecture, and I realized that the problem was not complete, therefore I stopped halfway. Read this problem one more time, please. And based on the solution I mentioned before, I would like to go back and explain it, because this is very important for you to understand when we're talking about the convective heat transfer. The top surface of the plate, mentioned the conductivity, is being cooled by air. Conductivity is given, while the bottom surface is exposed to hot stream at 100 degrees with a convective heat transfer coefficient 30. Okay, therefore we know this value here, and we know this value here. Okay, this is mentioning the steam. The temperature is the steam is 100 degrees, and heat transfer coefficient is 30 degrees. If the bottom surface here, that this temperature T1 is 80 degrees, asking you to determine the temperature gradient. The question here, what is the gradient? What is the slope? Okay, in the air and temperature gradient in the plate here. Okay, therefore we are trying to find the temperature gradient in the plate. Okay, top surface. Therefore that's what we're trying to find out. We mentioned this first. Whenever we like to solve any problem, we make a sort of set of assumption, and we did because one of the reasons is very important here is when we are trying to use a sort of some of the information equation, but those equations we are using is based on a certain assumption. Therefore, that solution is only correct for that given assumption. And one of the assumptions we made in development was we assume is a steady operating condition. It means the boundary condition will not change. It's always the temperature of the air and temperature of the steam remain the same. The velocity remain the same. We also assume the physical properties. In this case, the thermal conductivity of the plate is constant. Okay. Therefore, if the conductivity changing, we cannot use that equation we use. Okay, we have to assume the conductivity is a function of the temperature. Therefore, we cannot take it off that integral. And also, convective heat transfer coefficient is constant. As we know that the conductivity is a function of Reynolds number, and Reynolds number change for the flow over the plate. But here we assume the average convective heat transfer to remain constant throughout. Okay, that's again. Heat conduction is solid one-dimensional. We know that probably in this case you have the thickness, and you have also the length. the temperature will change, okay? But we assume it's one-dimensional and it's only in the y direction, okay? We can assume it's constant along the x, okay? And non-slip condition, and because it's, again, we're assuming the velocity is 0, therefore we have a boundary layer, a boundary condition, a boundary profile. Therefore, based on that one, we can also find the boundary profile for the temperature. Therefore, these are very important that we understand why we are making this assumption, because all of our equation, when we develop, it was based on this assumption, okay? Therefore, when we are trying to upload this equation, that means these are the conditions we made, okay? Again, what, as I mentioned, amplification here, there is heat transfer from the solid. Here is just on the surface, a pure conduction, okay? This is from lecture that we had. I show it here to you because that's one of the assumptions we made. And we may assume the convective heat transfer from the surface to bulk of the fluid, T infinity, from T surface to infinity, is the same as boundary as heat transfer conduction through the boundary layer, not through the solid. I'm talking about the boundary layer through the solid, okay? And that's we define in this here. We assume K is constant because this is the equation we can use here because K is constant, we took it out. Otherwise, the form of equation will be different, okay? And therefore, we can mention the convective heat transfer. It means H Ts minus T infinity, temperature of the surface to temperature of the bulk, infinity, is equal to conduction to the boundary layer, and that referring to that boundary layer. This is the temperature profile, and here the conductivity of the fluid, in this case, the conductivity of the air, okay? And therefore, by using this equation from here, we were able to define H is this divided by temperature heat difference, okay? Therefore, that's the assumption we make here. This is, again, conduction through the boundary layer, not through the plate, okay? The conduction to the plate and here. This is we cover in the beginning of lecture, this equation 6.3 and 6.4. And going back to the problem we're trying to solve, the same thing here. Just let me put it under here again. My computer change it again. The convective from this hot steam to the plate is the same as convective heat transfer from the plate to the air. Okay, because why? Because we assume it's steady state is the heat transfer from here is the same as with solid through the same as boundary layer and through the same convective. This is the equation that we have. And if I put here convective from here to here is represented by this one. Again, H of steam, the heat transfer coefficient, temperature of the fluid minus 21, okay? Because the fluid is 100 degrees, this 80 degrees. And H, we know that. And this is the same because it's steady state, therefore the same amount of heat goes from this plate to this infinity. Therefore here is from the T2 to minus T fluid. And that's exactly the same as amount of the conductive heat transfer to the thin layer of the boundary layer that we have here, okay? Therefore, if I can calculate, if I know the temperature profile here, therefore there is a temperature profile, we agree on that one. If I find the temperature profile and evaluate that value at y equals 0, give me how much it transfers. Therefore, any questions so far, please? Okay. Any question, Wolf? Okay.
Could you go to last slides for 1 second?
My friend, I have been here almost 5 minutes ago. Let me go back a slide. Okay. Here's last slide.
Perfect.
This is from 3 lectures ago, my friend.
Okay, I'm good now. Thank you.
Okay. Therefore, we can put this one here and we can calculate. Therefore, by equating here, this equation that I have, this one equals this one is equal to this one, okay? Therefore, I can calculate easily H of air here by equating these two equations here, by this equation here is equal to this divided by here. And since this is equal to this one is equal to this one, I can write for rather than this one right here, the infinity that I have, this is the K, and from here, I can calculate my temperature profile that I needed. This is the unknown component. This is the unknown component. Okay, if I calculate the temperature profile here because I'm air, this divided by this. Again, I've mentioned this convective to the air is the same as convective to the steam, and that's come from here. This is exactly because of from here. Okay, I do not know this one. I do not know this one, but I know this one and this one. Now I know the H stream because mentioned the problem. They gave the value. I know the temperature T infinity is 100 degree. It gave us the temperature of the plate is 80 degree, and the conductivity of the air is given. Therefore, from here, I can find the gradient, means the slope of the line at the boundary layer. If I do that, and I end up like this, okay? If I can find this value right here. This was convectivity transfer, temperature of the steam, temperature of the plate, and this one. And the same thing we can do it for the steam. Again, this equation is correct all the way. I can calculate here, and for the steam, I can find it become 2.53. Okay, and for this is the way, the whole idea behind here, that we understand we're talking about a steady state scenario. And now whatever heat transfer from the plate went to the surface is the same as going from the surface to this and so on. Okay, therefore we can calculate this temperature right here. Okay, any question, please? Go through it. If you have any question, again, let me know, okay? Therefore, this is the gradient of the temperature, in the air. And this is the gradient of the temperature in the plate. Okay? Conductivity plate, conductivity air. Okay? Okay. If you have done, let me go next slide. Done? Okay. Let's look at this problem. As I mentioned here, this is the general formula of Nusselt number. In general, we always write in this format. Just something for your information. Most of the work has been done in the area of heat transfer is experimental. Therefore, they are carried out by different type of fluid at different velocity, and they calculate the heat transfer, and from here they were able to find this expression. Therefore, this is the equation we all the time we use it, okay? And sometimes you will see some of this coefficient is not 0.5, 0.2. There are something because they try to fit the curve in a given equation. Now, a rectangular bar with a characteristic length of 0.5, okay, dimension given, is placed in a free stream where the convective heat transfer is 100 watt per square second. And this, when the free stream velocity were 25 here. Therefore, when we have the velocity 25 meters per second, the convective heat transfer is that much. When the velocity is 5 meters per second, the heat transfer coefficient is this one, okay? If the Nusselt number can be expressed in this format, where M and N are constant, determine the convective heat transfer, convection transfer coefficient for similar bar when the L is equal to, and velocity is here, and when L is 2 and the velocity is here. Therefore, we have a bar the length is 0.5 meter. And when they change the convective heat transfer, when they change the air velocity from 25 to 5, convective heat transfer coefficient change from 100 to 50. In general, we can express the Nusselt number as a function of a constant. I do not know what that means, what that value is. M, the exponent for Reynolds number, I do not know what that is. The Prandtl number N, I do not know what that is. I would like to calculate the convective heat transfer coefficient for a similar bar if the L is 1 meter and the velocity is 5 meters per second, and if increase the length to 2 meters and the velocity is 50 meters per second. Any suggestion? Since all of you, the camera off, I cannot see your faces if you're awake or sleeping or. Any suggestion? Therefore, we assume that we are not changing the gas. We are using for the same fluid. Therefore, since it's not given, we assume there's the same fluid. What we're trying to do here is trying to find this, because he's asking us to calculate exactly what is the heat transfer coefficient. The heat transfer coefficient is equal Nusselt number HL over K. Therefore, here this represents HL over K. Reynolds number, we know is velocity and characteristic length is given L. And since the fluid is not changing, therefore the viscosity and it's not changing, but we know the velocity. And the Prandtl number is the same, again, because we are talking about the same type of fluid. Therefore, what I can do here, I can write this expression for the two scenarios. I call it Nusselt number 1, Reynolds number 1, Prandtl number is Prandtl number, and Nusselt number 2, Reynolds number 2, and so on. The C remain constant. Therefore, I have two scenarios, 5 meter, 25 meter, and I know the heat transfer. And since I write it down, therefore the conductivity is the same, characteristic length become H1, H2, okay? Therefore, we're trying to use this expression, trying to find the value that we needed for other scenario, when L increased from 5 to 1 meter, and when the length increased to 2 meters. Let's go and see what we can do. Therefore, this is the general equation that we have. We have the Nusselt number is given to us is equal to coefficient C, Reynolds number to power M, and Prandtl number to power N. As I mentioned, I'm going to replace those definitions with the term that we know. That way we can simplify the equation. Therefore, I have Nusselt number HLK. I have Reynolds number, velocity times characteristic length. Again, if we are talking about the plate, the characteristic length is length. And here is kinematic viscosity. And here is kinematic viscosity and so on. Therefore, here. Therefore, if I write it down for two scenarios, as I mentioned, I know for the first case, the length is 0.5, the velocity is 25, and this one's 100. In the second scenario, the length is still the same, velocity is 5, and this one here. Therefore, I can place this number in this equation and try to see what I can do. If I do this one, I will end up this two equation, H1L1, K2L2. Velocity, therefore, I write this expression for scenario 1, I write it for scenario 2, and I divide them together. Therefore, this we can simplify to this one. Again, please do it in your paper to see if you can get the same result or not. Because if I write it down for H1, L1, velocity one, this one, and here is the same. And if I write for the second one, again, this one, when I divide them together, K and K will be cancelled, kinematic viscosity will be cancelled, and since this is only a characteristic of the fluid that I'm talking, the same will be cancelled. Therefore, this equation for this scenario will come like this. The first thing I can do here, I can find the M, okay? Because I know H1, I know L1, I know H2, I know L2. Therefore, that's all of the thing I know. From here, I can find them. Could you please find out the value of the M? Give me a number, please.
.43, something like that.
Let's see. You got this far? We put the number H100, L, this one, and 25, L.5 here, this one. And from here, we can calculate the value of M. If I go next slide. You're right, sir. You're correct, sir.
One
Absolutely.
second, sir. Can we go back to the last slide? Sorry, I'm just not done writing.
Yeah.
Thank you so much.
As you write, please ask any question. Okay? If it's not clear, please ask me to explain it.
Okay, I'm done. Thanks.
No problem. Therefore, now we have this scenario, we find the value of M. Let's go back to the problem. Therefore, I know this value, M. C and 1. Now I have to determine the convective heat transfer. That was not the question. The question here, calculate the convection heat transfer coefficient for the same bar, it means, with L equal 1 meter and V equal 5. Still, I have not found the answer to this one. I calculate the M, but how can I calculate this value? Now assume that you know the M. Please spend some time, think about it, and let me know how we can calculate the value heat transfer coefficient A. The question asking you, A, what is the value of H for this scenario and H for this scenario? Could you spend some time and put some effort in the paper to tell me what is, how we can do that for? And for what we did, with this one, and we got this 4. Now I'm trying to calculate the value of H1 when the length increased to 2 meters. Is there a way I can do that? Again, keep in mind, if this is the general equation, but the Prandtl number is only a characteristic of the fluid. And in all the scenario, we are using the same fluid. Therefore, the Prandtl number remains the same, okay? And now you have the base two scenario that use these two scenario and the calculated value of the M. But now he's asking us to calculate for third scenario, we call it case number 3. We know the velocity and we know the length. In this case, the unknown is h2. Can I go back and use this expression? And rather than writing for case 1 and 2, I write it for the case 1 and 3. And as I mentioned, case 3 here is I'm trying to find the value of h3 for scenario that I know the velocity and I know that case. Okay, let's go back. Let's say this is my scenario number 3. The length is 1 meter and the velocity is 5 meters. Okay, therefore here I can go back and mention I have no a case scenario 3 that in this case the length is 1 meter and the velocity is that. Okay, in this case the value unknown here is h3, but I know now what is the value of m. Okay, I know the value of m is this one. Okay, did you get it? Did you get it?
Yes, sir.
Excellent. Tell me what is the value, madam?
Sorry, I'm still working on it.
Sure, I take your time, please. Therefore, we place them here, as I call it this one, the case that I'm looking for. I know the n. This expression is just the same expression that we had at before here. The same expression. In this case, I do not know the value of h here. For this equation, if I remove 1, become in this format. Okay, this is exactly the same equation that we have here. Okay. We know, for example, with case the number 2 here, I know the heat transfer coefficient. I know the length. For this case, it was 0.5, but for the case I'm trying to calculate, the length is equal to 1. Therefore, VL here 5 and here. Therefore, we place this equation here, and we can calculate the heat transfer coefficient is 32.5. Now, could you please do for the last one, at least? Therefore, again, the same equation, you can use it. And then you put the appropriate length that we needed. This length, and this length. And still you can use case 2 as your base. Okay. Therefore, I can use the same now. In this case, I'm trying to calculate the heat transfer coefficient for the case L is equal to 2 meter. Velocity is 50 meters per second. Therefore, I use the same equation. This is my base that I use the information for 2 and trying to calculate for this. And you can see as the velocity increase, that your heat transfer coefficient increase. As the length increase, your heat transfer coefficient increase. Okay. Therefore, that's something. The whole idea that you're trying to understand the convective heat transfer problem and what exactly is happening. You have to understand, if you increase the length, your Reynolds number will increase. In case of plate, in the case of plate, as the length will increase, the Reynolds number will increase, okay? But you saw it last lecture when we were dealing with flow between two plates, okay? Between two plates, the velocity merge and the velocity profile remain the same. That's why in the case of pipe, use a characteristic length as R, and that remain constant, okay? Therefore, this is something that you have to slowly get better understanding of the convective heat transfer problem. Any question, please? Any question? Okay, let me move to the next problem. Now look at this problem. We go to chapter 4. Again, every so often we go back and forth just to help you as you read and as you do the problem, you have a much better understanding of the application. Again, please, it's not a question of memorization, trying to understand the problem. I do not know if you solve this problem in the class or not. We have a 5 centimeter rectangular ice block. Therefore, it's rectangular, it means 5 by 5 by 5. And the conductivity of the ice is 2.22. And alpha is equal to this 10 to minus 7. Initially at minus 20 degree, is placed on a table on its square base. The room temperature is 18. Therefore, you have a block of ice on a plate on the surface, and this is heat transferring to the air. Okay, that's exactly what we're trying to do. Okay. Now, the room temperature is 18 degrees. The heat transfer coefficient, it means the heat transfer coefficient, convective heat transfer coefficient between ice and air is 12 watt per square meter per degree. Read this part. Disregard any heat transfer from the base to the table. What that means, I don't know. Determine how long it will be before the ice block starts melting. Where on the ice block will the first liquid droplet appear? Therefore, giving you a lot of information. Therefore, you're dealing with ice as a solid material. That all the physical property has been given to us. Conductivity, thermal diffusivity is given. The initial temperature of the ice is minus 20. You place this ice in a room. The temperature is 18 degrees. And there's a convective heat transfer between the ice and air. It's telling us we can ignore the heat transfer from the base. I do not know how that information is useful to us. And it's asking us how long would it take the ice to start melting. And your own experience, where will be the first place the ice start to melt? This is something you should think about. Okay, now you do it when I will sit down and watch outside, okay? Where we should start? We mentioned chapter 4.
Biot number.
Pardon me?
Biot number.
Bio number, okay, bio number, but I don't know, but you calculate bio number, what should I do?
Well,
Good point, good point, but what
we have
should
more
we do?
than one to do.
Okay, let's calculate the bio number.
but then I'm not sure to what to compare after. But there's a table, but
No, you can calculate the BO number is equal to K, is H, is
yeah, but
12.
after, I mean.
No, as you calculate H is 12 times K is 0.22, and L is equal 5 centimeters. 12 times 5, 60.6 divided by this, and I believe it's more than 0.1. Therefore, it means I cannot use simplified equation.
So you could use the equation for 452,
And,
which is
tell me what is the equation, sir? I take it, whatever equation you say, I will take it.
it's a transient heat conduction for multi-dimensional system.
Okay,
Because
good.
it's not a long or infinite wall, so you have it's a rectangular bar
But-
where
Yeah, therefore the question that I have here, I have a solid material. Let me see what is the camera here. The solid material placed on the plate, therefore is a three-dimensional problem. Because heat loss from this side, heat loss from this side, heat loss from this side. Is not a long plate. Therefore, this is two-dimensional, three-dimensional problem. Therefore, I have to find out, because I'm losing heat from this side, I'm losing from this side, and losing from the top. And since all it is rectangular, therefore the heat transfer from the three plate is the same. Therefore, this is a three-dimensional problem. Therefore, you have to go in this multi-dimensional, you use the multi-dimensional technique. But the question here is, where should I start? It mentioned, the problem here is mentioned that I can ignore the heat loss from the bottom, okay? I can ignore the heat loss from the bottom. How that can help me? And the solution I have here is symmetric. Heat transfer from this side is the same as heat transfer from this side, okay? Therefore, this is the scenario I have to look at here. He's telling me that I ignore this part. Mathematically, what that means to me and to you. How can I use the information given here? Disregard heat transfer from the base.
it's one-dimensional
No.
in the y-axis.
No. But again, remember the solution we develop, we assume is symmetric. This condition here is the same as the condition here. The solution that we have is symmetric heat loss on both sides. But now he's telling me there is no heat transfer here. What that means?
The conduction is 0. Well, it's insulated, so the conduction is
Insulated. Insulated. What that means? Good. Insulated. That means heat loss is 0. Now, how can I modify my problem to use the solution that I have? Can I assume?
Like a boundary condition.
Say it louder, please.
It's like we have a boundary condition
Yes.
where at this point the flux is 0, so we can use this as a reference.
Can I assume? We mentioned that means there is, if I put it here that you can see it here, I assume here this side there is no heat transfer. Disregarded means there is no heat transfer. Can I assume that rather than having a 5 centimeter here, I have a 10 centimeter, that the same condition takes place here? Therefore, if I assume it's 10 centimeter, at this middle, x equal 5, there is no heat transfer. Therefore, rather than assuming the 5 centimeter block, I can assume 10 centimeter block, but I have heat transfer from both sides. Okay, that's the concept that we can use as symmetric. Therefore, when I assume it's symmetric, assume it means the heat transfer from this side and this side are the same. The convective heat transfer this side and convective heat transfer the other side is the same. Okay. Therefore, again, the problem we have this, we know how to solve it, but we have to start from the right place. Let me go step by step, please. Read this one. Please read this one. I do not know if it mentioned 5 centimeters. Why I changed it to 12 centimeters? I'm sorry. Okay. Why? Why change it to 12? Let's forget about the length of this moment. Probably let me go back and check again the question. Is this one?
Isn't it the cube 4x4 or?
I do not. I'm trying to check because I've sometimes mentioned 4x4 or 5x5. I don't know why that's for 10. Textbook is 5 centimeters. Okay, let me see.
I
Maybe-
think the question.
Okay, the height, I'm sorry. Okay, that's correct. The height, but the square base is 4 by 4. Okay, okay, correct. Okay. Therefore, here we can assume this one. Okay. The rectangular block can be treated as short rectangular. What that means is short, it means that we cannot ignore any dimension. Therefore, you have the heat transfer from all 3 different sides or 6 sides. Okay. Therefore, we can assume this is a plate symmetric that now we can assume 2 centimeters. Okay.
Professor, I
Yes,
have
sir.
a question. I'm not sure to understand why we're doing this type of mirror. Like, I don't get it.
Good. Let me go back because I'm trying to figure out that problem here is, let me go back. Just give me a second, please. Let me go back. Let me go back to my lecture that I have. Chapter 4. Remember in this chapter, we solved this one for the scenario that we have a long plate.
Yeah.
And we mentioned this, the solution that we find based on the boundary condition, that this is for the plate, the thickness is 2L. From here to here is 2L. And the center is at x equals 0. This is x equals 0, therefore this length is L. The length from here is L. And that's the boundary condition we develop, okay? And we mentioned that at this x equal L, we have convective heat transfer. This is convective heat transfer. Therefore, you have heat loss from this surface and also heat loss from this surface. Both of them is by convection. Therefore, with this equation, represent the heat transfer to this solid, this temperature profile to this solid, okay? But we assume that this is a symmetric system, x0, xl, x0, xl. Both of them are at the same condition, okay? By assuming that this is a symmetric, the condition, both of them are the same. Therefore, at x equals 0, you have no heat transfer from this side to this side, no from here to this side. We call it, this is a symmetric plate. You agree?
Yes, I agree.
Okay. Therefore, based on this boundary condition, we were able to solve this problem and find the answer to this one. And therefore, the answer we find here is representing this figure that you have right here. Again, here, this is for a plate. We assume here this is symmetric, and we were able to use this graph to find the temperature at the center. or we were able to use this equation here and find the temperature at the center, right here, or any point right here. Therefore, this solution that we have developed, all of them was based on this assumption that we made here. This is symmetric. Now, this problem is trying to tell us, here it mentioned, is we have a piece of ice, and the piece of ice, the block of ice that we have, at one side, there is no heat transfer. Therefore, I cannot use this solution for that one. What I can assume that my ice is, rather than, let's say, 5 centimeter or 6 centimeter, is 10 centimeter. That there is no heat transfer at this point. Therefore, I use this solution because this solution gave me this temperature profile from here to here, and the temperature profile from X to L is the same as from X to L here. Therefore, I'm using this idea that rather than having a block that has L thickness, it has 2L thickness. And I use the solution for that one. Did I answer your question? If it's not, tell me, I will explain it again.
I get it perfectly. Thank you.
No problem. Therefore, we go back here and we're trying to use this one. Therefore, the block it mentioned, I don't know what I use, 12 centimeter, and that has to be 10 centimeter, okay? The thickness of block can be treated as a short rectangular block that can physically be formed by intersection of two infinite plates. Therefore, as you mentioned, this is a two-dimensional problem, three-dimensional problem. Therefore, this comes from the, again, if, let me go back again to tell you why. Again, what that means, we are trying to use this scenario. Yeah, you're trying to solve this problem, okay? Block of ice. You're trying to look at this block of ice that we have. And this is, since it's two-dimensional, we're trying to find the temperature in this plate and temperature in this plate, okay? Therefore, first we assume is that in this direction is infinite, the thickness is B, and then we assume that in this direction is the A and in infinite. Therefore, this block of ice is the result of the cross-section of these two planes that we have, okay? Therefore, that's why we mentioned when we're trying to look at here, we're trying to look at for a plane wall. Therefore, here that is we have here, right here, okay? Therefore, we assume it is one dimension in this direction, trying to find the temperature, and then we assume one dimension this here, find the temperature. Therefore, we have to find where exactly we're trying to calculate the temperature, okay? And we mentioned here before, here is, we did this problem, this problem, let me get it here. Here, we assume, for example, for the cylinder, we assume that a cylinder is a result of a wall and a long cylinder. The same thing we are trying to do it here, okay? Let me go back here. At this moment, forget about this number. This rectangular ice block can be treated as a short rectangular block that can physically be informed by intersection of two infinite plates. One, 2 and 4 centimeter, the other one is 10 centimeter. I will come back here. X is measured from the bottom surface. Again, X is measured from the bottom. This surface represents the adiabatic center. Again, if you like, I can go back to what I mentioned. Because it's half, now we have to look at 2L, we add another. And that's, the other point here is melting start at the corner of the top surface. Again, this is something that when you start to look at here, is asking you how long it will be before the ice block start melting. Which one? You consider the top surface, which one you start to first start to melt here, or here, or here. Therefore, you have to have some, be able to sort of have some idea where is the best, the most possible place to start to melt. Okay, this is something that, because that then we go and start to do the calculation for that point. Therefore, here is melting start at the corner of the top surface. Why top surface? Why not the bottom surface? Now, so we need to determine the time required to melt ice block, which happen when the temperature reaches 0 degree. Therefore, we're trying to calculate how long it takes the temperature here at this top corner surface to become 0. Okay. Why not here? Because here we assume it's adiabatic, is not here. Therefore, there's a thickness right here, the bottom. Okay. Therefore, we're trying to find the why. Why not here? Tell me why not. Why is here? Okay. Therefore, that's something that you have to, either you have to do a try and error at different place and to see which one is faster. Okay. But physically, we can mention the top corner because it's the intersection of the outside in this part and this part. There is more high possibility to have it melting at this point. Okay. Therefore, we start to look at here. First, we calculate for the wall. Mentioned 4 by 4 is 2L is equal 4. Therefore, L is equal 2. Okay. The reason, again, do you know why is this one? Because we assume the thickness is 2L, and our reference is at the center. Therefore, the L becomes 2 centimeters. And if you look at calculate here, is your BO number is more than 0.1. Okay. Therefore, you cannot use the simplified equation. Okay. Now, please go back to look at your textbook. Table of I do not know is 4.2 or 4.3. And for the wall, they gave you a lambda 1 and A1. These are the coefficients. If you have no idea what I'm talking about, if you have not reached chapter 4, let me go back and explain to you again one more time here. Again, they were trying to find a solution for 2-dimensional. But we assume is that this 2-dimensional problem is the result of 2 1-dimensional infinite plate. And we were able to solve that problem and trying to find the solution. And the general solution, it was this one. Okay. This is for any BO number, for any Fourier number. This is difficult because you have to calculate lambda and here, and therefore we mentioned in case if your tau is Fourier number, not BO number, tau is more than 0.2, you can simplify that equation to this equation. This is for a wall. And if you look at this equation, you have 2 constants. We have one value here and one value exponent here. They're right here, lambda 1 and A1. And the value of these 2 for the scenario, tau is more than 0.2, can you find that in table, I believe 4.2, if I'm not making a mistake, okay? Please go and check if you can see that number, okay? Okay. Again, I mentioned when our understanding here, this is a 2L. If we mention 4 centimeter, it means the thickness is 4 centimeter. And the L is from the center to this one, that's why we mentioned 2 centimeter. Therefore, we come back here and we look at the solution here. Therefore, here we find for the wall that the dimension that we have base 4 by 4. Therefore, we're trying to look at here the BO number, L is equal to 2 centimeter, and this value given the problem, the conductivity of this for ice, and this is for the air conductivity, and this one last here. And then we look at the wall number 3. Again, that's 5 centimeter is because the whole thickness. What we assume is adiabatic. We made it a case that you have another layer here, because in order to have a symmetric scenario, here we assume it's on the top of the plate, and there is no heat transfer. But I don't have the solution to this one. The solution I have here, I have for a wall 10 centimeter. Okay, that's why it's my 2L, 10 centimeter, my L become 5 centimeter. Therefore, that's why here we divided by 2, here we kept that, because we assume here is symmetric, okay? And we find this point value is again is more than 0.1. Therefore, I cannot use a simplify equation, okay? I cannot find simplify equation. Again, I have to go back to table 4.2, and again, I do not know it's 4.2 or 4.3, and find the value of lambda 1 and A1. Therefore, now I can go back and use the equation. Now the equation, which equation should I use, okay? Therefore, we go to table 2.4. We do not know the time. Therefore, I cannot calculate the Fourier number. Therefore, I do not know if I can use table 4.2 or not. Therefore, what I have to do, I can make an assumption that my Fourier number is more than 0.2 in order to be able to simplify equation, okay? Again, please be patient with me. I'm trying to make an assumption that I can use this one, this table here, okay? I'm trying to use this equation, okay? I'm trying to use this equation, but I do not, the only time I can use it if I assume tau is equal to 0.2. In order to calculate the Fourier number, if you remember, is alpha t divided times time divided by thickness. But that I do not know the time, I cannot calculate the Fourier number. I assume it is the case, and I start to use the equation I want here. This equation gives me the temperature at any point. This gives me the temperature at the center, okay? Therefore, I'm trying to look at the surface outside, okay? Please ask me any question that you may have, okay? If it's not clear, please let me explain it right now. Therefore, I can go back and use this one, okay? This is what we explained. Again, please understand why here we divided by 2, because it mentioned 4 centimeter. I divided by 2 because L, and here I kept 5 centimeter because it's symmetric. That means I'm looking at from the top to the center. I assume symmetric, okay? And I make an assumption. This is less than 0.2, more than 0.2. Therefore, I can simply use simplify equation. And the equation I use here is like this. L1, L2, L3. This is 3-dimensional problem, okay? Therefore, I only look at 2 volts here because we mentioned symmetric. Therefore, I'm trying to calculate the temperature as mentioned in the corner top here. I'm trying to measure if this is one plate. I'm trying to calculate the temperature at this point. And I look at this side, I'm calculating this one. Therefore, I'm looking at the sides, okay? And if you, as I mentioned here, is tau, again, here is a ratio of the temperature. The temperature that I would like to calculate if we as the melting occur, it means 0. The temperature of ambient infinity, again, please let me go back. I don't want to lose you here. Look at this expression that I have here, okay? The one I have is trying to look at for each scenario. But I have to push once and I put it here. Be patient with me, please. I have to put it here. That's why I made a mistake. Okay. Therefore, this is your tau. That you're calculating the temperature at the edge. Therefore, L1 and L2. Okay. This is your T infinity given 18 degrees. This is the initial temperature of the ice is 0 degree, and here is 18 degree. Okay. Therefore, the temperature C is this one. Okay. And we're trying to calculate. Therefore, here we go step by step again, and here the equation. Here is the temperature that melting occurred, ambient temperature, initial temperature here. This is looking about one surface, and this is related to this surface, because I'm trying to find out when the temperature at this point becomes 0. Okay, this equation for one plate, this equation for one plate.
Sorry?
And we calculated A1 and A2 from both parts here. Okay, we have this one and we have this one. Okay.
Sir,
Explanation? Yes, sir.
can you just remind me what number, example number that is?
The problem this is from your chapter 4.
Chapter 4, even
Yes.
with a 3D wall?
3D what do you mean?
3D wall.
This is from the textbook, end of the
Okay.
chapter. I don't know if I got the
Oh, okay.
end of the chapter, and that's a problem. I believe it was 4:110.
Okay, perfect. Thank you. Thank
No
you so
problem.
much.
Okay.
Sir, can you please go back to the previous slide?
The previous, this one or previous, that lecture number 4.
No, this one.
This
The
one.
previous one where we had the L's. Yeah, that.
This is 10 centimeters. This has to be 10 centimeters. I made a mistake.
Okay.
Okay, this is my 10 centimeters. It is 10
Perfect. Thank you.
I had a question as well.
Yes, yeah.
How come, can you explain again why we consider the intersection and not just the top or not just the side?
Physically, if I look at just, again, if you look at this is your wall, this is your eyes, okay? Can you see it, the slide? Can you see the screen?
Yes,
Yeah.
yes, sir.
Now, look at the temperature on the surface here. The heat transfer to this point is from this side and from this side and from this side. Okay? Therefore, there are conduction coming from this two different sides to this point here. But if you look at the surface at this corner here, in this corner, there is less conduction coming from the other side because here and here is more exposed to air. Therefore, there is much higher possibility that the melting occur in this corner. Because if you look at in the plate in the center, if you assume at the center, the worst case either happen here at the edge or at the center. Do you agree with me? It has to be in the surface first. Do you agree with me that the melting occur on the surface?
Yeah.
Do we agree? Okay. Now, either happen on the plate here, anywhere, or at the edge. If you look at, let's say, the worst case scenario at the center, on the top surface and the center. If I look and move it like this, you have conduction through the ice in this direction, and you have conduction coming here and conduction here. Therefore, there is conduction from zero, from minus 20 to that surface. Therefore, there is a lot of conduction coming to that on the center here. But if you look at the corner here, rather than center, if you look at the corner, this part, there's more energy exchange to the environment than any place on the surface.
Right, I understand. Thanks.
Okay. Therefore, we assume that case, okay? But we can always go back and verify our answer, okay? Therefore, I assume at the edge, therefore, I'm looking at L equal 2 centimeter and L equal 5 centimeter, okay? Therefore, that's what we have done it here. I'm looking on the edge. I'm looking at the edge. And based on that one, I found these two numbers. Then, as I mentioned, this block of ice made of 2 infinite slabs, as we mentioned before. Therefore, I'm looking at a case. This is one slab that has such a dimension, and there's another slab made of this dimension. And we multiply them together, we end up finding to this solution. Again, remember, nobody asked me why I multiply this is to power 2. Why I made this one power 2 and this one power 1?
It's because it's 2 dimension. It's more dimension.
3 dimension, right? 1, 2, 3 dimension. 2 of them are the same, and the other one is 5 centimeters. Therefore, that's why this is representing one block, 4 by 4, and here representing 4 by 10. Okay. Therefore, we calculate here, we put the number, and we find the T here. Again, T comes from this part of the equation right here, that we have this number, tau, is my Fourier number. This is my Fourier number right here. This is my Fourier number. When we place them here, what happened here? We can calculate the T by putting the number that we have for alpha here. We can find is after almost 1,292 minutes. It means almost 21 hours. Therefore, tell us that after 21 hours, start to melt. Remember, the temperature ice originally was -20. Okay, but now there are 2 points that we have to remember. First, we assume is at the corner. We can go back and calculate the center. Probably will be longer. And also, we made another assumption that we use the equation from table, the simplified equation. We selected only the first term. I have to go back and calculate my Fourier number, and to make sure if I made a correct assumption, because I assume Fourier number is more than 0.2, therefore I use simplified equation. Therefore, I have to go back and verify that concept. If I calculate my Fourier number, it's become 0.384, and that represents is more than 2. Okay. Therefore, here is the only thing. Verify assumption 2 hours, 20 hours. So we can make it 24 hours. Therefore, any question? Please go back and read the problem, and to see if any part is not clear. Let me explain it to you. I can go back, well, if you have not finished writing, I can go back to that page, okay? But going back, I believe this is, I check in my, I have a still 5th edition, because they're supposed to send me 6th edition. I haven't received it. I do not know where it is sitting. That's from 410. I'm sure there's a similar problem in your chapter 6th edition, okay? And again here, have you finished this part? Have you finished?
Yes, sir.
Okay. If you have not, I can leave it there, and then I go to the next slide.
How did you because the question was asked for the corner, can you repeat how you implemented that assumption in the formula?
Let me go back to this one, the previous one, the equation that we have. Remember, this expression that you have, you can calculate the temperature at any point that you would like.
Okay.
Okay. In X here, if I put X equal L, it means on the surface. Okay. Therefore, I use this equation here, and as I mentioned, I want at the top corner, right? And let me see if I can. Top corner, it means at the surface here. At the surface here. That's why. In this case, here it is this this corner. Let me just go this corner. This corner in the top surface, this surface, and this surface. And since it's a cube, this surface is the same as this surface. That's why we put it to power 2. And the top is different. Okay?
Yeah, thank you.
No problem, sir. Therefore, if you are done with this page, I can go to the next slide. Therefore, here we have the equation for the 2 sides and the bottom side here. And then we put the number that we have, A1, lambda 1, and for Fourier number, we have here, we place them, and we calculate the times become 21 hours. It's around more 20 hours, okay? And here we have to go back and verify that assumption if this assumption is correct or not. And the assumption was we assume the Fourier number is more than 0.2. We take this time and put it in the equation for Fourier number. And Fourier number is alpha thermal diffusivity of ice was given. The temperature was given. And L is 5 centimeters. Therefore, that shows this is almost 0.235. Therefore, this is the worst case scenario. The worst case scenario, why I mentioned worst case scenario? Because for the other plate, is this becomes 2. Okay? Therefore, if it's 2, this number becomes much more. Therefore, this that we put at the size, it was a thickness 10 centimeter, and L become 5. Therefore, we look at the worst case scenario, and we can see it's important. Okay? Therefore, this is again, we come back. Technically, we finished chapter 6. We finish chapter 4, chapter 5, and chapter 6. And we come back every so often. We look at the some of the problem. We discuss it too. The only time this problem will be useful to you if you've gone through the chapter and read and you're familiar, then you can ask me some question. Otherwise, there's no use. Okay. Please start to read it. Chapter 2, 3, 4, 5, 6, and today you have also tutorial, and I believe he's going to do the problem from chapter 5 or 6, because I give them the solution for both. And if you have any question, ask them or ask me. Any other question?
I have a question.
Yes, sir.
So I remember when we did the Bayet number, we had to verify if it's less than 0.1 and then do the calculations. But in this problem, we assumed something and then verified is tau if tau is greater than 0.2.
Sure.
Let's say if it's less than 0.2, what would happen then?
If less than 0.2, therefore you have to go use the table.
Okay, and the graph.
Yeah, and if you want to go to that one, it become like this. Let me show you. Then you have to use this one few times, okay?
Yeah.
Because you have temperature, you have the one BO number, and you find here you find tau value, okay? Because you have to calculate one plate to other plate, and so that becomes a little bit time consuming. But the other worst case scenario that you have to use this expression here, and then it's become much more difficult.
And for that example that you mentioned, you can't just use that. Well, you need to use two tables, right? Because you need to determine the temperature at 0 first, and then after at the corner.
Yeah, and that's exactly what we have to do it for each wall. Okay, and that's become a little bit more complicated than using equation. Any question about your project?
Just question, please, before the project. Did you send us already chapter 5 and 6 solutions? I didn't get that.
I did not send it to you, sir. I sent it to TA. If you have any question, because I would like to make sure that you read. I have the solution. I can send it to you right away. But I prefer at least you try to do one or two problems, because the whole idea is to develop some confidence, because I don't want you to look at the solutions, oh, it's easy. Try to finish the chapter, try to do one or two problems, and then we send you the solution. Because you have to have develop a certain confidence that you know the subject.
Okay.
If you look at the solution, you think, oh, it's easy, you are not really going to beyond your capability. I will send it to you over the weekend from chapter 5, I have no problem. But please read the chapter, try to do one or two problems, ask me, ask TA to explain to you, and then we send you the solution.
Okay.
Any question? If not, the lecture is finished. Thank you very much. I will be here for the next 5-10 minutes, and I will be happy to answer any question. Have a nice evening.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.
Excuse me, sir. I have a question regarding my project.
Yes, sir.
So I got the feedback from the marker, and he said that my indoor temperature reflects, it's like too similar to the outdoor temperature. Do you know where I could have made a mistake for that to happen?
Of course you can make a mistake, because the question, the only time the temperature indoor is exactly as the temperature outdoor, when you have no person inside the building.
Yes.
And then you have infiltration. Probably you did not include the energy generated by the people inside the building. Probably you did.
I did that.
I know you did it, but it wasn't really reflected in your program. Okay, you can probably, when you try to calculate, and that's why I always mention, when you do simulation, also not only write the output, also write the input to make sure that the input that you have actually was used in the program. Okay, because you have given some value, probably in your program that value was considered 0, therefore there is no heat generation from the person inside the room or from the activity with the computer and so on. Okay, and that's shows that this way your